All right. Sorry about that, everybody. Story goes, I actually ended up recording yesterday for at least a good hour, and my setup looked correct. It looked good. Uh, I checked everything at the time, and I don't know, everything looked like everything was gonna go well. But then what ended up happening was after I had uploaded the video, I had absolutely no audio. I don't even know what went wrong. Today I redid my OBS settings and things like that, and it looks like I'm getting audio again. So I hope that you know uh, whatever I'm saying is actually being heard. And I've already tested test recording this time around. Um, Yeah, unfortunately, I don't want to. I mean, okay, so actually, there's two things that came out of this. Like, first is a good thing is that the original video, I was fumbling around again trying to install the development environment that I'm going to just quickly summarize for everybody. And so that's good. This time you'll just get like a quick overview, and then if you have any questions or whatever, just post in the comments. By the way, I'm really happy to see that everyone's actually interested in this series. I don't know, it just makes me very excited to kind of just go over this stuff even more. Second thing is that the git clone for the source was actually very slow too. And so I'm gonna spare you of all that because it's already done. And so we'll spend a few minutes today just going over like the development environment necessary to actually start developing with our kernel. Um, and I'll give you the motivations behind that. And after that, we'll just proceed as normal. The reason why this setup is a little complex is because I maybe don't know of a better way. Because I'm not like a sysadmin or I'm not really expert C developer or anything like that. In fact, I'm still learning. Um, this book is written in 2009, I believe, when Kernel 2.6 was still like the latest kernel series. So the thing is that that's like a really long time ago, at least 15 years ago. And I am pretty sure if I were to clone the kernel tree and then build it and then install it on my regular system, I would wreck my system. And so the way I'm thinking about this is that I can actually do kernel development on this system that I'm streaming from and then do the building and testing and installation, whatnot, in a VM that runs natively on a 2.6 kernel, like a VM that is running a distro that was built on a 2.6 distro or 2.6 kernel. And that makes sense to me because then I'll minimize the chances of actually messing something up pretty badly. And also, I can always create backups of a VM and then like restore it later if I really mess up. And so that's like these are all like advantages, right? Another advantage is that I can, I we can clone our kernel source to not on this drive, but actually on another VM, set up as an NFS share, so that this way we can actually work off the same on this computer we're going to be working off the source, right? But on the VM where we're going to build the kernel and install it and do all that stuff, we're going to actually access that same NFS share. So they're going to be like linked together. And how I'm thinking about it is Scala draw is something like this type of infrastructure. And I don't know why my tablet is not cooperating for some reason. So otherwise I'll just use a mouse. Yeah, I'll just end up using a mouse. Okay. So how I'm thinking about it is I have this NFS share running a VM. So this is going to be TrueNAS. Ugh. Let's thin this out a little. Stroke width. TrueNAS. Okay. And then I have like my dev machine. Access this, right? And then the VM will actually be running Ubuntu 10.04, which is really old. It's like Lucid Links or something like that. And that will also tap into the same share. So now I could do all my development and store all my sources and resources in here and just kind of just act as if it was local, but not really. As far as like my VMs are set up, I'm using a Proxmox instance. I just have two VMs set up here. It's relatively simple. One running TrueNAS, and then another one running Ubuntu 10.04. And what this will allow me to do is I can just back up these VMs, and then if I really mess up and I can't recover, I can always just reload them. So I suggest that's like a model that everybody should do, just so that they don't waste like a lot of effort after getting set up properly. So yeah, so as far as the TrueNAS goes, it's just a simple NAS share. So I have this listening on a specific IP. And if I were to go here and just kind of, I think I can just log in as root. I'm not sure. Yeah, yeah. It's just a matter of creating a user. So if I am, I think if I were to go to, shoot, I already forgot credentials, I think. Users, credentials, users, create a user and make sure they're mounted in the home directory. And then what you can do is you can actually create a new share, an NFS share, and then just actually create it to that home directory, pointing to that home directory, and then set the appropriate permissions here. So in this case, I have it just be able to map to a user and a group, and then you should be able to map it from your computers. And how I've done that is actually, if I were to go to my FS tab, so I can just do, let me clear this first. Like do vim etc fs tab. What I have here is an entry specifically pointing to my NFS share. So the first entry here is just the path, like the IP, and then the path to the NFS share, and then basically where you want to mount it. So I've created a folder called Linux-dev under my code directory, which is under my home directory here. Specify NFS, give the defaults, and then when you want to actually mount without restarting, you can just do sudo mount -a, okay? And then before you know it, you have a share. So I've already cloned the 2.6 tree to spare everybody the wait. I know I'm here in the correct place in my NFS because I have this like bash rc and profile, because that's like the home directory of that user that I created on the NAS. Okay, so yeah, once you've gotten set up here, all we need to do is actually get set up with Ubuntu 10. And I've done most of that here already. So, you know, it's just basic installation. But what you want to do is that since it's such an old version, you kind of want to actually update it just slightly to the point where it's manageable. Of course, it's still going to be out of date because it's not even supported anymore. But what you want to do is to go to Software Center and then uncheck everything here, because that's going to be annoying. Like when you do sudo apt get update, it's always going to want to hit these non-existing places. Okay, so what you want is to want to add sources and add basically everything relating to like security updates and main package updates or main packages in general, right? So all you need to do is just add, and then you'll type something like deb, right, for deb packages, and then http no s old-releases.com, and then you'll just do slash Ubuntu, and then after that, it's just the repo names, so lucid main, and then just hit add source, and then you can just add everything going from like main multiverse restricted universe, and then you do lucid hyphen updates main multiverse restricted universe, and then all the security for the same thing. I think I had universe twice. I'll just remove that. Okay, so when you close, it'll actually attempt to do apt get update automatically. And then what you want to do after that is just to do uh, sudo apt get dist upgrade, and then it'll try to just get packages. I've already done all of that. So hardware wise for this VM, I've specified 12 CPU cores, 8 gigs of RAM. And then I'm going to change this. Like I have the disk for IDE, which is fine. I needed that for Ubuntu 10 to actually detect the disk, but I also did E1002 for just for the sake of being able to detect some sort of network adapter. I'm going to change this back to whatever native thing it is, which is going to be the Vert IO. And I think now after updating and doing all this stuff, it's actually going to support that network adapter. So interestingly enough, Ubuntu 10.04, when it's fully updated, is using the 2.6.32 kernel. And that's good because whatever kernel we're going to be on, which is 2.6.34 based off of this book, is technically like an upgrade, right, of the kernel. So that'll allow us to look at and do some interesting things because it's worthwhile in this case. Okay, so we have a basic Ubuntu setup, and we also have our NFS share. What I want to do is I want to show you the exercise again after I'm going to change my network adapter and mounting the NFS share using FSTab on this VM side. I could do SSH and all that stuff, but it's actually harder to do because this Ubuntu 10 is using like a different encryption compared to my Arch install, and I don't want to deal with all that stuff. But I shouldn't have needed to deal with all this too, so I don't know. Maybe I like doing things the hard way. So anyway, I've changed this to be the Vert IO. Okay, Vert IO para-virtualized. I think all this is okay, so it's fine. So I'm gonna start up the VM again. And by the way, I really like Proxmox, so it's one of the best hypervisors out there. There's like so many resources in learning how to learn do Proxmox. One course I recommend is Jay LaCroix's Learn Linux TV. Um, he is a very good channel. I recommend. I learned a lot of my Linux stuff from him. He has a whole course on Proxmox. So let me look for it. I recommend, where is it? Right here. From zero to Proxmox. Is super good. Like I watched all his videos and I learned a lot, and I learned how to do everything I know how to do here from those video series. So Jay LaCroix's Proxmox video. And then also, if you really want to learn more about like Linux server administration, he has like a book called Mastering Ubuntu Server. It's a free plug for him, like because he's like just reading his material and trying his stuff has like taught me so much, and so yeah, I recommend his book here, Mastering Ubuntu: Gain the Expertise and Art of Deploying, Configuring, Managing, Troubleshooting Ubuntu Server. Okay, anyway, so here I am. I have a fresh install of Ubuntu. Oops. With I guess now network that should work. Yeah, it should work. Next thing I want to do is I want to show you how I'm going to mount my NFS share. here virtually, since I've already done it on my Arch machine here. So I think it's simple. I think all we need to do is uh, just do nano, I think, because I don't have Vim here. I don't think Vim is here. Okay, well, we'll do that too, but let's wait for that soon. Okay, so let's do nano, sudo nano, etc fs tab. Okay, so we have our fs tab here. It's very simple. Oops, I'm already on Vim mode. Fs tab here. So all you have to do is just add the entry so that it's mounted on boot. So my IP for the server is 192.168.1.132, and then the path will be mnt pool average dev. Okay, and I want to mount that to home. I think I just chose Roger as my username, and then I'm going to mount that as average dev directly. And now I need to create that folder. You can't mount it without creating the folder. So we'll do that after this. So we'll do nfs default 00, and then we'll save in nano. Okay, and we'll exit. And then we'll do make dir average dev inside our home directory. And then if we did that here, we should see average dev up here. Now that we've had our fs tab updated, I think it's just as simple as sudo mount-a bad super block missing coefficient helper program. Okay, so we need to install NFS on this system. So let's just install some programs now, some packages, whatever. So okay, let's just do sudo apt get install. Let's do NFS. I think it's called NFS common. Okay, so let's do that to get NFS support. So NFS common. Okay, and then we'll need. Okay, let's just see if mount works now. Sudo mount a. Okay, that looked like it worked. Okay, so if we were to cd into average dev on our local machine here now, and we ls, we actually see the Linux 2.6 code that we had cloned, and we'll go over cloning later. Now, I want to install additional packages here. So what we'll need on this system is we're going to need sudo apt get install. We're going to need git core, because that's what the git package was called back then, just so that we can actually create branches and stuff like that locally. And then we'll also need build essential. Okay, we always need build essential, and it'll give us the right versions of the tooling we need to actually build our kernel. We'll need Vim, because I like Vim. And then we can get what else? Oh, we'll need something called ncurses dev. That's very important. That's actually for later on when we're actually configuring our kernel to be built. More on that later. And then I think that's all. That's all for now. It's as simple as that to grab the necessary dependencies. So we'll just do that. Then, so we'll need, yeah, so I think this 2.6 kernel needs GCC 4.4, which is what it's going to be installed, it looks like. And then Vim is always handy. Okay, so we're almost fully ready. You know what? Let's come back to here as we need. We're in a good place. If I were to go into Linux 2.6 now and I did git status, I hope it works. It'll say something. It takes a while. It's a big tree. Okay, it should work. It's a test, right? So, um, anyway, it should work. So, I'm just gonna leave it be, and let's actually now we're at a good state where we have a VM setup for just like regular development, and then our NFS share mounted on both sides and all set up correctly. Let's just go and read and then do all the other stuff later as we go along. We had to do some grub stuff too, so we'll just come back to that later. Okay. Oh, see, here we go. On branch master, nothing to commit. So we're good. All right. So let's do it. Getting started with the kernel. Okay. So water break. In this chapter, we introduce some of the basics of the Linux kernel, where to get its source, how to compile it, and how to install the new kernel. We then go over the differences between the kernel and user space programs and common programming constructs used in the kernel. Although the kernel certainly is unique in many ways, at the end of the day, it is a little different from any other large software project. Obtaining the kernel source. The current Linux source code is always available in both a complete tarball, an archive created with the tar command, and an incremental patch from the official home of the Linux kernel, http kernel.org. So here is actually where all the existing kernel code is at. You can actually browse through it through web interface like this. And you can also see that it has all the most recent versions of the kernel. So the latest one right now is actually 6.12, but the kernel is actually in various forms, such as like LTS, stable, things like that, right? So stable version right now is 6.11.9. LTSs are all down here, going all the way down to 4.19. And so if you really think about it, for these LTSs, any like security patch that's necessary will actually get put into here in these various versions. So this is a good place to just look at the kernel archives. And I think you can actually go and find older versions too, or even other people's trees. So yeah, good place to go and just peruse. But we're not going to mess around here too much for the time being. So yeah, just keep that in mind. I think you also can just browse like some, what is it? Yes, this is how all these releases work and things like that. So yeah, unless you have a specific reason to work with an older version of the Linux source, like us, you always want the latest code. The repository at kernel.org is the place to get it, along with additional patches from a number of leading kernel developers. Using Git. Over the last couple of years, the kernel hackers, led by Linus himself, have begun using a new version control system to manage the Linux kernel source. Linus created this system called Git, with speed in mind. Unlike traditional systems such as CVS, Git is distributed and its usage and workflow is consequently unfamiliar to many developers. I strongly recommend using Git to download and manage the Linux kernel source. You can use Git to obtain a copy of the latest pushed version of Linus's tree. So we've done this. We've done Git clone all of this into actually our NFS. So since I'm in my NFS right now, I have actually done a Git clone here to actually get the Linux 2.6 tree directly off of Linus's tree. So if I cd into that and I git status, that's pretty much it. Detected dubious ownership in repository, blah 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 blah. It doesn't matter. Let's just do that. Add safe directory here. C, Control V, whatever. Okay, so now it's gonna do its little crunching again. Okay, so when checked out, you can update your tree to Linus's latest Git pull. So with these two commands, you can obtain and subsequently keep up to date with the official kernel tree. To commit and manage your own changes, see Chapter 20 Patches, Hacking, and the Community. A complete discussion of Git is outside the scope of this book. Many online resources provide excellent guides. Okay, so I think for Git, we don't need to know too much if you're not familiar with Git. I hope by now you are. It's it's already 15 years later, pretty much. But really, you just need to know how to do like Git checkout, Git commits, maybe Git reset, stuff like that. We're not really pushing to anywhere. We're just going to work off locally as we're, you know, going through all this. So installing the kernel source. The kernel tarball, which is the GZ file, is distributed in both GNU zip, gzip, and bzip2 format. Bzip2 is a default and preferred format because it generally compresses quite a bit better than gzip. The Linux kernel tarball in bzip2 format is named linux-x.y.z.tar.bz2, where x.y.z is the version of that particular release of the kernel source. After downloading the source, uncompressing and untarring it is simple. If your tarball is compressed with bzip2, run tar xbjf linux-x.y.z.tar.bz2. Okay, we don't need to care about that because we've cloned the entire tree. So if it's compressed with GNU zip, run this command tar xvzf linux-x.y.z.tar.gz. Again, we've cloned it. We don't need to download the tar files. So yeah. This uncompresses and untars the source to the directory linux-x.y.z. If you use Git to obtain and manage the kernel source, you do not need to download the tarball. Just run the git clone command as described and Git downloads and unpacks the latest source. Okay. Where to install and hack on the source. The kernel source is typically installed in /user/source/linux. You should not use this source tree for development because the kernel version against which your C library is compiled is often linked to this tree. Moreover, you should not require root in order to make changes to the kernel. Instead, work out of your home directory and use root only to install new kernels. Even when installing a new kernel, /usr/source/linux should remain untouched. Cool. Using patches. Throughout the Linux kernel community, patches are the lingua franca of communication. So patches are kind of like the pull requests in the Linux world, I guess. Yeah. You will distribute your code changes in patches and receive code from others as patches. Incremental patches provide an easy way to move from one kernel tree to the next. Instead of downloading each large tarball of the kernel source, you can simply apply an incremental patch to go from one version to the next. This saves everyone bandwidth and you time. To apply an incremental patch from inside your kernel source tree, simply run patch-p, I guess PL or P1, redirects your patch file as std into the script. Generally, a patch to a given version of the kernel is applied against the previous version. Generating and applying patches is discussed in much more depth in later chapters. Cool. So we don't need to worry about generating the exact patch files now. We'll just hack around and see where we go from there. So anyway, the kernel source tree. The kernel source tree is divided into a number of directories, most of which contain many more subdirectories. The directories in the root of the source tree along with their descriptions are listed in table 2.1. So here are all the folders. So we have Arch, which is architecture specific stuff, like if you're on like x86, ARM, x86, 64, those types of CPU architectures. Code like really relating to that will probably be in here. Things like crypto, which is not like Bitcoin or anything like that. It's more like any cryptography APIs in here. You have documentation, you have drivers. So again, Linux is like mostly a monolithic kernel, so you can actually either statically link, like compile the drivers with the kernel, or you can actually load them up separately as like libraries, or I think you call them modules. You'll have file system code, you'll have a bunch of headers. Yeah, you'll have a lot of stuff. Kernel is where we're going to have all our main like kernel related things like process scheduling, things like that. memory management, network code, samples, so we can add demos here, sound, tools, and then virtualization stuff. This is exciting, just like reading this. So we were to go back to here, and we just ls, right? We have the same thing here. Let's do lsla, and we'll see it. So yeah, it's the same type of folders. So should be similar. Okay, so a number of files in the root of the source tree deserves mention. The file copying is the kernel license, GNU GPL v2. Credits is a listing of developers with more than a trivial amount of code in the kernel. Maintainers lists the names of the individuals who maintain subsystems and drivers in the kernel. Makefile is the base kernel makefile. And again, I don't think we need to understand all this deep just to get started. So good news, I guess. Okay, so building the kernel. All right, we're getting there. Building the kernel is easy. It is surprisingly easier than compiling and installing other system level components such as glibc, which is I think the C standard library. The 2.6 kernel series introduced a new configuration and build system, which made the job even easier and is a welcome improvement over earlier releases. So configuring the kernel. Because the Linux, so I preview on this section is talking about like configuring the kernel to be built. There are reasons why, because kernels can be customized in a way where you can actually remove features or even add additional features that are considered to be like optional, specific drivers, or take away drivers that you don't need to be compiled. So then you can actually really optimize your kernel for specific needs and purposes. Like for example, I think there's like a gaming optimized kernel nowadays, which probably has like optimizations and compilation compiled code just related to making games run faster, or you can like compile something just for like no printing or whatever. So that's the reason why you would need to configure your kernel. I think this session will also discuss like how other distros do it to today. You know, where they are compiling a kernel that is able to run on everybody's computers, pretty much. So anyway, configuring the kernel. Because the Linux source code is available, it follows that you can configure and custom tailor it before compiling. Indeed, it is possible to compile support into your kernel for only the specific features and drivers you want. So just like what I said, you can take things out, you can add things in. You basically get to tailor your kernel the way you want it to be. And I think that's like the coolest thing about Linux is that you get to decide what you want in your kernel. And this is like back in 2009 too. So we were already doing this. I wasn't, of course. I just barely got started, but people were doing this, and I really appreciate that now. Configuring the kernel is a required step before building it because the kernel offers myriad features and supports a varied basket of hardware. There is a lot to configure. Kernel configuration is controlled by the configuration options, which are prefixed by config in the form of config-feature or config_feature. There we go. For example, symmetrical multiprocessing, SMP, is controlled by the configuration option config_SMP. If this option is set, SMP is enabled. If unset, SMP is disabled. So that means if you were to kind of disable SMP, you can't use multi-threading, I'm guessing. Yeah, like, yeah. I'm not sure why you wouldn't want that, but okay. The configure options are used both to decide which files to build and to manipulate code via preprocessor directives. So I'm assuming that if you take out a lot of stuff from your configuration, you can actually get faster compilation times. My guess. We can always measure that. Configuration options that control the build process are either booleans or tri-states. A boolean option is either yes or no, meaning true or false. So you can either have it or not have it. Kernel features such as kernel preempt are usually booleans. A tri-state, meaning three options, okay, is one of yes, no, or module. Okay, so either you have a yes, you have a no, or you have a module, or M in this case. The module setting represents a configuration option that is set but is to be compiled as a module. That is a separate dynamically loadable object. So Linux supports modules, meaning that you can compile something that will actually be loaded, not with that full kernel binary. So remember the Linux itself is like one big C program pretty much, but you can actually load this separately. You can compile things to load separately. In the case of tri-states, a yes option explicitly means to compile the code into the main kernel image and not as a module. Drivers are usually represented by tri-states. So drivers are usually compiled with the option to be loaded as modules as opposed to just being within the kernel binary. Configuration options can also be strings or integers. These options do not control the build process, but instead specify the values that kernel source can access as a preprocessor macro. For example, a configuration option can specify the size of a statically allocated array. Okay, so this is the interesting part here, vendor kernels. So distros, okay, like Ubuntu, Fedora, those types of things. They're kernels. Vendor kernels, such as those provided by Canonical for Ubuntu or Red Hat for Fedora, are compiled as a part of the distribution. Such kernels typically enable a good cross-section of the needed kernel features and compile nearly all the drivers as modules. So that is the reason why it can get really good coverage across a variety of hardware, because they're compiling all the drivers available in the source tree, but then they're doing it as modules so that it doesn't get huge. This provides for a great base kernel with support for a wide range of hardware as separate modules. For better or worse, as a kernel hacker, you need to compile your own kernels and learn what modules to include on your own, which is not bad. I think for us, since we're on a virtual machine, we're compiling it for a virtual machine. It should be very simple. The hardware is very generic in this case, so it should be okay. Thankfully, the kernel provides multiple tools to facilitate configuration. The simplest tool is a text-based command line utility called makeconfig. Okay, make config. So we type in our source tree, make config. We're going to get a program that's going to prompt us through things. So this utility goes through each option, each one of those config underscore options, one by one. It'll ask you, do you want this? Do you want that? Do you want this? Do you want that? Okay, and ask the user to interactively select yes, no, or tri-states for module. Because this takes a long time, unless you're paid by the hour, you should use an ncurses-based graphical utility. So remember we installed the ncurses dev package. This is what allows us to render this tool here. It's a text user interface, terminal user interface, whatever you call it. So it'll allow us to kind of pick and choose what options we want graphically, and then build our configuration file that way, automated. Or we can use a GTK plus or GTK plus based graphical utility with make gconfig. So we're going to use make menu config instead. I like this tool. I think it's really easy to use. So I'll show you how to use that. These three utilities divide the various configuration options into categories such as processor type and features. You can move through the categories, view the kernel options, and of course change your values. Okay. And this command creates a configuration based on the defaults of your architecture. Make def config. So I think def stands for default, based off of whatever your architecture is. So it'll just choose what's best for that specific platform. Although these defaults are somewhat arbitrary, on i386, they are rumored to be Linus's configuration. So if you choose i386, you'll get whatever Linus ends up using. Fun fact, I guess. They provide a good start if you have never configured the kernel. To get off and running quickly, run this command and go back and ensure that the configuration options for your hardware are enabled. The configuration options are stored in the root of the kernel source tree in a file named .config. You may find it easier, as most kernel developers do, to just edit this file directly. So you can generate the file out of any one of these tools into a .config file. Then you can open it up, and then you can add more options or tweak them further. Okay, so it's quite easy to search for and change the value of the configuration options. After making changes to your configuration file or when using an existing configuration file on a new kernel tree, you can validate and update the configuration using make old config. Okay, I don't think we're going to be doing this a lot. Okay, so I don't know. We'll see. You should always run this before building a kernel. The configuration option config _ik config _proc places the complete kernel configuration file compressed at /proc/config.gz. This makes it easy to clone your current configuration when building a new kernel. If your current kernel has this option enabled, you can copy the configuration out of /proc and use it to build a new kernel. So you can use zcat /proc config.gz, output that as .config, then you can do make old config. Okay, after the kernel configuration is set, however you do it, you can build it with a single command called make. Okay, unlike kernels before 2.6, you no longer need to run make dep before building the kernel. The dependency tree is maintained automatically. You do not need to specify a specific build type such as BZ image or build module separately as you did in old versions. The default makefile will handle everything. Cool. Minimizing build noise. A trick to minimize build noise but still see warnings and errors is to redirect the output from make output to this file, whatever you want, pretty much. If you need to see the build output, you can read the file. Because the warnings and errors are output to standard error, however, you normally do not need to read the output, basically. So then you can just throw it into dev null. So make output to /dev/null. This redirects all the worthless output to that big ominous sink of no return /dev/null. So that's like a special location where it's kind of like the abyss, right? You could throw any output to that place and it just goes nowhere. So okay, spawning multiple build jobs. The make program provides a feature to split the build process into a number of parallel jobs, so multi-threaded, multiple instances. Each of these jobs then runs separately and concurrently, significantly speeding up the build process on multiprocessing systems. It also improves processor utilization because the time to build a large source tree includes significant time in I/O wait, time in which a process is idle waiting for I/O request to complete. Okay, by default, make spawns only a single job because make files all too often have incorrect dependency information. With incorrect dependencies, multiple jobs can step on each other's toes, resulting in errors in the build process. The kernel's make files have correct dependency information, so spawning multiple jobs does not result in failures. To build the kernel with multiple make jobs, use make-jn, where n is the number of jobs to spawn. The usual practice is to spawn 1 or 2 jobs per processor. For example, on a 16-core machine, you might do make j32 to dev null. Cool. So we have 12, so we can just do 24. We'll see how fast that goes. I think we'll be limited by our NFS bandwidth though, but I have 10 gig, so who knows? Oops, I told everyone to have 10 gig. Not internet, just Ethernet. Okay, so let's hold off on installing kernel. Let's actually try and build this thing now. Okay, so the first thing I'm going to do is, since I'm in this kernel tree, let's be on our build computer here. Let's actually do git checkout. Let's check out actually the 2.6.34 branch. So we can do git checkout v2.6.34. I believe that's what it looks like. So if we were to do that, I hope that works. Or is it? Actually, let's look it up. Linux 2.6 Git. Okay, what was it? This is like a mirror, so we can trust it. Tags will be okay. V 2.6.34 exists, so it does exist. Okay, great. So I did the right thing. So this then, okay, so it's checking out now. I should have done this earlier. So now we have to wait. How long we have to wait? I have no idea. So I guess we can keep reading. We can keep reading while it's checking out. Okay. Good to do it now. Okay. So let's just go to installing a new kernel. Installing the new kernel. After the kernel is built, you need to install it. How it is installed is architecture and bootloader dependent. Consult the directions for your bootloader on where to copy the kernel image and how to set it up to boot. Okay, that's okay. I think I know how to do it. I can walk everybody through this one. At least for Ubuntu 10. Um, Always keep a known safe kernel or two around in case your new kernel has a problem. I can help with that too, so that's good. I am useful. As an example, on an x86 system using Grub, you would copy blah 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 arch i386 boot bz image to boot and name it something like VM Linux version and edit boot grub conf, adding a new entry for the new kernel. So we can actually automate this. It is actually automated. Systems using Lilo to boot would instead edit Lilo conf and then rerun Lilo. Installing modules, thankfully, is automated and architecture dependent. As root, simply run sudo, and this is as root, right? Sudo make modules install. This installs all the compiled modules to the correct home under lib modules. The build process also creates the file system.map in the root of the kernel source tree. Okay, it contains a symbol lookup table mapping kernel symbols to their start addresses. This is used during debugging to translate memory addresses to function and variable names. So like a source map, pretty much. Okay, we're making progress. 34%. Okay, so a beast of a different nature. The Linux kernel has several unique attributes as compared to a normal user space application. Although these differences do not necessarily make developing kernel code harder than developing user space code, they certainly make doing so different. So here's like some things to keep in mind when we are developing in kernel land. Okay, it's different than normal C. Okay, so these characteristics make the kernel a beast of a different nature. Some of the usual rules are bent, and other rules are entirely new. So we're gonna have to keep an open mind as we're learning. Okay, there's gonna be a lot of things that are really weird. I'm guessing that's what they're saying. Although some of the differences are obvious, we all know that the kernel can do anything it wants. Others are not so obvious. The most important of these differences are, first, the kernel has access to neither the C library nor the C standard headers. So remember, no standard C here, no like stdio in kernel land. No printf too, I'm guessing. The kernel is coded in GNU C. I think we're okay here. I think that's what we've always been doing. The kernel lacks the memory protection afforded to user space. So there's no like concept of your own virtual address space as a user process, meaning that you're going to be able to access memory in a way where you're not the only one running in the system anymore. Um, the kernel, and I think also like allocating memory too is different. So yeah, the kernel cannot easily execute floating point operations. Okay, that's a weird one. The kernel has a small per process fixed size stack. Okay, I can live with that. And the kernel has asynchronous interrupts. It is also preemptive, meaning that it can actually be queued up to run and supports SMP. So therefore, synchronization and concurrency are major concerns within the kernel. So the fact that it supports concurrency and it's preemptible is actually a recipe for a lot of race conditions and deadlocks if you're not careful. Mainly because you have to write code in a way where you assume like any point in time. Oh, did I freeze? Oh no, did I freeze? Oh, okay. Yeah, hold on. Okay, so what I was saying is that the thing is that the kernel is preemptible, and then you can also have um, concurrency, right? And so you have to take into consideration that you can the kernel is executing code at any point in time. It can just be like preempted, switched out at any point, right? And other processes can like take over, like so that can like mess up data. And portability is important. So okay, so then they're going to go in detail about all these things, but let's check back on our checkout. Okay, still going. And by the way, the kernel is huge. Like I tried doing this once before where I cloned the kernel and opened it up in IDE, like VS Code, and it just had a hard time. So, um, yeah, this is not surprising me where it's like trying to update a bunch of files. So, anyway, so what does it mean when kernel development you have no access to libc or standard headers? So unlike a user space application, the kernel is not linked against the standard C library or any other library for that matter. There are multiple reasons for this, including a chicken and the egg situation. But the primary reason is speed and size. The full C library, or even a decent subset of it, is just too large and too inefficient for the kernel. Do not fret. Many of the usual libc functions are implemented inside the kernel, so it's re-implemented pretty much. For example, the common string manipulation functions are in lib string C, so lib in the lib folder in the kernel. So you have all of them in here. Just include the header file linux slash string.h, and then you can just use it as normal as any other regular C program. Okay, header files. When I talk about header files in this book, I am referring to the kernel header files that are part of the kernel source tree. Kernel source files cannot include outside headers, just as they cannot use outside libraries. The base files are located in the include directory in the root of the kernel source tree. For example, the header file linux slash inotify.h is located at the include slash linux slash inotify.h in the kernel source tree. Okay. A set of architecture-specific header files are located in arch slash the specific architecture. In this case, for us, it's going to be x86-64 slash include slash asm in the kernel source tree. So for example, if compiling for the x86 architecture, your architecture-specific headers are in arch slash 86 slash include slash asm. Source code includes these headers via just the ASM prefix, for example, ASM ilctl.h. Okay. So, of the missing functions, the most familiar is printf. The kernel does not have access to printf because printf is part of the C standard library. Okay, but it does provide something called printk, which works pretty much the same as its more familiar cousin. So printk is our printf in kernel development world. Okay, so the printk function copies the formatted string into the kernel log buffer, which is normally read by the syslog program. The usage is similar to printf. So you just do printk hello world, whatever, then a formatted string and all the arguments necessary to replace format. Looks like printf. However, one noticeable difference between printf and printk is that printk enables you to specify a priority flag. This flag is used by syslog-d to decide where to display kernel messages. So here's an example of these priorities. Print K, current error. This is an error. Okay, so this is like it's like a macro, I guess, maybe? Since we don't have a comma here, I'm guessing. Yeah. So note there is no comma between current error and the printed message. This is intentional. The priority flag is a preprocessor defined representing a string literal, which is concatenated onto the printed message during compilation. We use print K throughout this book. Okay, good to know. So this is actually just like a preprocessor macro that will eventually be replaced and make it look like valid C. Almost there. Okay, GNU C. Like any self-respecting Unix kernel, the Linux kernel is programmed in C. Perhaps surprisingly, the kernel is not programmed in strict ANSI C. Instead, where applicable, the kernel developers make use of the various language extensions available in GCC, the GNU Compiler Collection, which contains the C compiler used to compile the kernel and mostly everything else written in C on a Linux system. The kernel developers use both ISO C99 and the GNU C extensions to the C language. Okay, these changes with the Linux kernel to GCC, although recently one other compiler, the Intel C compiler, has sufficiently supported enough GCC features that it too can compile the Linux kernel. The earliest supported GCC version is 3.2, GCC version 4.4, or later, which is what we have, is recommended. The ISO C99 extension that the kernel uses are nothing special, and because C99 is an official revision of the C language, are slowly cropping up in a lot of other code. Okay. The more unfamiliar deviations from the standard ANSI C are those provided by the GNU C. Let's look at some of the more interesting extensions that you will see in the kernel. These changes differentiate kernel code from other projects which you might be familiar with. All right. Let me just take a talking break. Okay. Come on. Wait, so it updates files. I don't know what it does after that in Git. It does something else. I forgot what it was. Oh, we'll see. We'll see soon enough. Okay. So what does it do? Let's see. You are in a detached head state. Blah blah blah. Okay, no, that's fine. That's fine. Detached head means that it's not really a real branch. This is more like a tag, so it's fine. I think it's that. Does it ever get faster? It doesn't, huh? Oh well. Okay, it gets a little faster. So okay, we're now in the 2.6.34 branch, and we're gonna get out of here for now. We're actually gonna go back to our VM, and we're gonna like kind of verify the same thing. I'm gonna try and make this bigger. In fact, you know what we can do? Let's do this. Let's pop this out. Can we pop this out? Yeah, we can pop this out. Let's send this to workspace 4. Let's go here, and then let's full screen. Can we full screen? Full screen? Yes, we can full screen. Okay. Okay. So we're here. LS. Everything's there. NFS, right? We can do the status. It should tell us that we're also in a detached head state, maybe. But let's see if we can compile the kernel after this. So let's just make sure that we're doing the right thing. By the way, if we ever want to watch our system, at least the VM, we can pull up System Monitor and see like CPU activity and things like that. One thing that, since we're working through an NFS share network, right, we're going to look at the network tab here just to look at network activity. We'll look at CPU activity when we're compiling, and then Yeah, memory is it's okay. I mean, this is like 2009. 8 gigs was plenty. 8 gigs was like super high. Anyway, so not in any branch. This is older version Git, so it's not gonna tell us as much. Okay, so we got trust that works. So the first thing we want to do, right, is we want to make our configuration file. I think it was just make menu config, right? So that should bring us a nice user interface after this process is done, where we can actually go through each option and turn them on and off and have them go into our .config file so that we can actually build the kernel. So I'm just going to give you an example here. Let's take a look at, for example, so you will have stuff here. You can literally just go in, enter like for every type of category, and you can just like disable things and enable things, whatever you want to do in here. So I am going to be fine with the processor type of features. Power management doesn't really matter here for me. Bus options, again, I don't really care. Um, let's do networking support. Um, I don't, so for example, like IRDA, infrared subsystem support. Like I'm pretty sure I don't need that, so I'm gonna turn that off. And M means module, right? And Bluetooth, no, I don't need that. For example, Plan 9 resource sharing support, probably not. RF switch, nope, probably not. So this is examples like how we can actually like make a lighter kernel, for example. Device drivers. This is fun, right? um, I guess I don't need telephony support. I also don't need ISDN support. I don't really need a lot of the support. For example, sound card, like all this here. It's also, I think, advanced Linux sound architecture, right? We don't need any of that. Well, I'll keep it there though. Memory stick card support, we don't need that. InfiniBand, no, right? Huh? And then, we can even like go as far as like graphics support, for example. We can turn off things. Like these are just drivers, right? So we don't have to like end up compiling them at all. So like for these, I don't think we need any of this because we're like in a generic uh, I guess VGA driver. I don't know what chipset it's based off of. I'm gonna guess some Matrox maybe. Let's just take a guess, but this is fine. We'll keep all these. So uh, for sure, I wish I had a 3D FX. So, but you kind of get the gist, right? Like this is not bad. Like this, I like this menu because it allows us to kind of just see things um, as we are actually, you know. So yeah, this is just an example of me going through and configuring things, right? Firmware, I'm just gonna keep that there. I don't know what I'm doing there. File systems, for example, like I don't care about ext2. Ext3 and 4 seems important. I don't think riser fs is useful. gfs, I don't need to think about that. xfs, no, I don't need gfs2. I don't need any of this. btrfs, unstable, nope, don't need it. All this, whatever. DOS, NT, whatever. So yeah, network file systems, we probably need that. That's our NFS stuff. Uh, so kernel hacking, that's useful. This is gonna give us like more options to do logging, for example, or like other things. This is whatever. You pick and choose. You pick and choose what you want. I'm just going to leave everything the way it is here. I'm pretty sure it's okay. Yeah. Yeah. We'll learn more. We'll learn. We'll learn. Okay, so let's say you're happy with everything you have here, right? You can just do exit and it'll ask you to save your kernel configuration and then you can say yes. So then everything is now going to be in a new file. We do lsla called .config. And if we were to actually go, let's do less.config, you'll see that this file has a bunch of flags. Comments are in the pound character. So for example, right here, this config k times scalar, is commented out, right? Local version is commented out. So this you can actually edit stuff here, and basically when you make the kernel or you build the kernel, it's going to use that .config file. So let's push our luck. Let's actually do that. So I'm going to do make -j. Since I have this is the book says to use whatever number of processors you have. They had I think they showed they had 8 or something, and then they did 16, something like that, right? So I'm gonna do 24 since I have 12. So you just do make J 24 on my system, and then it's gonna just do stuff. So I can actually choose to sit here and watch. So it's pulling down like configuration, and let's watch like our CPU utilization and all that stuff. So it always makes me nervous that it's taking this long to start because I don't know if I'm doing it right. But yeah, it looks like we're getting good usage. I can see that. Uh, and of course, like you're gonna see some network activity because of NFS. So let's actually just wait and see a little bit of this to gain some confidence that we're actually doing something correctly. It should just kind of like work on its own, right? Um, so let's see. And compiling it the first time is always gonna take a while anyway. There's so many things to be built. It's a big project. So probably I don't know where it stands as like the size of the code base in comparison to other big software projects, but definitely probably the biggest people will ever see in their life. Unless you're working on some other things at some other big company, for example. So yeah, let's see. It would give me some confidence if this actually moves. So it looks like there is CPU activity. So maybe the crypto thing just takes a while. And after that, it should be pretty smooth. So my plan is I'm just gonna like after we gain some confidence to let it build, let's just like leave it building, and then I'm gonna end the video, and then tomorrow we'll or whenever we'll come back and then we'll do the rest of the steps. Uh, Grub needs to be updated, and I'll show you how you can actually get it so that you can select different kernels in the menu for Ubuntu. But yeah, this is totally making me nervous here. Okay. Should we continue to read then? Yeah, let's read a little more. Okay. Okay. Okay, so inline functions. Inline functions. Both C99 and GNU-C support inline functions. An inline function, as its name suggests, inserted inline into each function call site. This eliminates the overhead of a function invocation and return, register saving and restores, and allows for potential greater optimization as the compiler can optimize both the caller and the call function as one. So I don't really know what that is, to be honest. We'll find out, I guess, as we learn. Um, as a downside, nothing in life is free. The code size increases, so that makes sense because it probably kind of slaps things on. Um, to various files because the contents of the functions are copied into all the callers. Yeah, that makes sense, which increases the memory consumption and instruction cache footprint. Kernel developers use inline functions for small time critical functions. Makes sense. Okay. Okay. Making large functions inline, especially those used more than once or that are not exceedingly time critical, is frowned upon. So don't do it. Don't do it. Okay. Okay, so large functions inline and which aren't used a lot and also not really critical in time. is frowned upon, maybe because it's confusing. An inline function is declared when the keywords static and inline are used as part of the function definitions. For example, static inline void wolf, unside long, tail size. Okay, cool. The function declaration must precede any usage or else the compiler cannot make the function inline. Common practice is to place the inline functions in header files because they are marked static and the exported function is not created. If an inline function is used by only one file, it can instead be placed towards the top of just that file. So let's create inline functions inside the .h files rather than in the C files. In the kernel, using inline functions is preferred over complicated macros for reasons of type safety and readability. Great. Okay, let's see where we at. Hey, we made progress. All right. So it was at that Intel thing. Now we're at this thing. Cool. Yeah, I mean, I think we just let it go. So yeah. Anyway, so yeah, let's just let this thing compile. I'm not gonna just sit here and watch, and I'm kind of tired from reading already. So um, yeah, we'll just like go see how long it takes. Um, maybe this whole NFS thing was not a good idea after, or maybe there's just some sort of bottleneck in the network. But I kind of find that strange because there should be more bandwidth than that. So I don't know what's up. Maybe I'll figure it out. But I'll just let it go. There's probably just some processing going on or something. Yeah, I'm like totally wanting to just kind of see why is it sleeping. That's so weird. Is there anything going on? Why is it sleeping? Uninterruptible. Huh. Actually, I do want to wait a little longer just to see. Why is this not going? Is there something wrong with this one here? Maybe? Let's see. It's just not robust enough. So, or it's just staying there. Yeah, there's like barely any CPU usage. Interesting. So it's not like it's not even really trying either. So I'm guessing there's just something wrong with, or I guess like the build system. What the heck? Oh, I click on here. So I think that's just the nature of the build in the beginning. Interesting. I don't even know what AS here is. It's all sleeping. I'm not even getting any activity too. Huh. But how much did it make progress? And let's see. It did do quite a bit. It did do quite a bit. Is it because there's just too many jobs? All right. Well, I'm just gonna leave it overnight, see what happens, and then go from there. All right. We'll check back tomorrow or soon.